Thank you. Good afternoon, everyone. I hope you are having a lively afternoon session so far. Did any of you read the brief for this talk before you foolishly walked into the room and sat down? A few of you did, okay. Well, if you didn't, I mentioned Taylor Swift quite heavily in the brief for this talk. I don't suppose we have any Taylor Swift fans in the audience. Okay, we've got a few proud people, awesome. Okay, well, what about, I won't make this all about music, what about Oasis fans then? Is anybody like a big Oasis fan? A couple of people at the back. Wonderwall, Don't Look Back in Anger, no? Gallagher Brothers? Okay, we've got a few nods, a few more people. This talk is not all about musical tastes, or more specifically, what the people in this room do not like from a music perspective, it would seem. But what Taylor Swift and Oasis have in common is that quite recently they have both either announced or been on tour. And these were quite literally events that generated not only a huge amount of hype and buzz about the fact that these people were touring and people were very excited about the music, but these were quite literal events that generated traffic and demand on IT systems that supported the ticket purchase process. Taylor
Swift was here for a weekend, so there was a big traffic.
Okay, good. I'm glad that Taylor Swift brought other countries to a standstill, not just the UK. I am not a Taylor Swift fan. I will say this now, just to set the scene. I'm not particularly passionate about Taylor Swift, but I am passionate about event-driven principles and how we can use them to challenge some of the traditional scaling models that we have with IT. So a few things that I want to talk about today. I do want to talk about Taylor Swift. I've not just mentioned her as a hook to get you in the room, although for this crowd I don't think it would have worked by the hands up at the beginning. But I want to talk a little bit about Taylor Swift. I also want to talk a little bit about event-driven scaling with Kubernetes and what that means, and different approaches that you might take to scaling workloads that you deploy to Kubernetes. So, to Taylor then. Unless you have been quite literally living under a rock, Taylor Swift has very recently taken the world by storm with her most recent world tour. And it is quite literally a record-breaking world tour. It's the highest grossing tour ever. It's well over $1 billion already, and they think it will reach almost $2 billion. So it's been bigger than any other musical artist in our lifetime that's done any sort of tour, including Elton John, if there's any Elton John fans here. He did a farewell tour, and he did not make as much money as Taylor Swift did. It shattered attendance record globally across the world. It's also resulted in a 40% increase in the friendship bracelet market. So if anybody is into any sort of arm jewelry, friendship bracelets are now even more popular than they were before, solely due to a lyric in a Taylor Swift song. So she's had a huge impact on the friendship bracelet industry. According to the US Tourist Board, she's also added a significant amount to the economy, and they estimate that's around 10 billion to the economy, and that's purely due to people who have purchased tickets for Taylor Swift concerts, and they travelled either to other cities, other countries, other states, and this is the money that's attributed to that, so their hotels, their taxis, transport, all of those sorts of fun things. And Taylor's fans, or Swifties, as they're also known, I'm going to use this term throughout the talk, so it's important we all baseline the term Swiftie now. They've also created an earthquake. So the jumping and dancing from Taylor Swift fans was with such force that it actually measured on the Richter scale, and it actually created what can be classed or classified as an earthquake. So this tour had a pretty big impact. But we knew it would have a huge impact before Taylor Swift ever hit the road, or before she sang a single note. So Taylor Swift fans, or Swifties, are extremely committed. And when Taylor announced her tour, most ticket merchants decided to have a dedicated fan pre-sale event that fans would pre-register for. And in the case of the Eras Tour, around 3.5 million registered for early access to Taylor Swift tickets. So if we think about the IT systems that are required to purchase a ticket, we've got 3.5 million people that really want it. So the ticket merchants thought, I don't want to deal with that much traffic. So what we'll do is we'll pop them into two buckets. Bucket 1, 1.5 million Swifties. Bucket 2, everybody else. So about prox 2 million Swifties. So if we think about this from an IT systems perspective, we've got a view as to how much demand, how much traffic we're expecting to hit those systems. So we can prepare ourselves. Now, of course, on the day, if you'd read any of the headlines, you will know that this is not what happened. It was not smooth sailing at all. Now, in fact, the IT systems that support the ticket purchasing process actually experienced 4 times the amount of traffic that they ever did under peak load previously. So there was a significant amount more traffic than our ticket merchants and our ticket retailers were expecting. And if Taylor Swift was to try and satisfy all the demand that existed for tickets for her tour, she'd have to go on tour another 20 times. Like that's how much demand there actually was. So it's unprecedented load on our IT systems that support this process. So could pre-scaling have helped here? So we already knew we had 3.5 million people interested, and we'd already agreed we'd have a couple of million that we would look at. You know, if we'd pre-scaled in advance, could we have handled all of this traffic? And there are some considerations to keep in mind here. And the first one is that it's sometimes really difficult to capture all of the input signals that we might have when it comes to pre-scaling. So in the case of Taylor Swift, it might not just be, actually, we've got this many people in the fan club. There might be other signals that are inputs that drive demand. Perhaps there is another event happening in the same city at the same time. People are holidaying in a particular location at that time, and that drives demand or extra population in those locations, which are going to drive demand up in those particular cities. Sometimes we do get our estimates around traffic wildly incorrect. So pre-scaling is great when we fully understand the demands that are going to be there, but where we get them totally wrong, that it's actually not useful at all. Equally, where we have our Taylor Swift fans who have decided to get their pre-sale link and then have that link open on their laptop, on their tablet, on their phone. They've shared it with mum and dad because they also want mum and dad to try and get tickets. They've shared it in their WhatsApp group, and all their friends are all going to share that link, and everybody's logging on at the same time. So actually very quickly, our 1.5 million fans turn into millions and millions and millions of session requests to purchase tickets. Where we also have IT systems in that journey that are, I don't know, slightly monolithic in nature and tightly coupled. We might be able to scale one part, but where we've got one part that doesn't scale so well, that part's going to bring everybody down. And it's important to note that there are lots of dependent systems in the journey from a ticket purchase perspective. It's not just our ticket retailer or our ticket merchant. There are other downstream systems that also all need to be playing ball and all need to be scaling in line with the amount of demand that's going to hit. So pre-scaling is great where it's really well understood in terms of the demand you're going to have, where you've got the architecture to support it, and where your downstream systems or your dependencies, again, are also well understood and can scale with you. But if we think about our Taylor Swift fans and the challenges that they encountered on the day when they wanted to purchase a ticket. So challenge 1 was even getting into the waiting room and getting access. But challenge 2, once ticket fans had added a ticket to their basket and they were going through the purchase process for those particular tickets, what they were seeing was a little pay now, click on it, and a little spinning icon, and then all of a sudden their transaction would time out. So worst thing in the world. They were so close, but yet they still didn't manage to get their tickets. And this part of the ticket purchase journey, if you like, isn't really something that's solely dependent on our ticket merchant. There are a load of other downstream systems that help support this payment journey. So if we think about that payment journey, let's break down the people that are in it. So we have our ticket purchasers, or our Swifties in this case. We have the card issuing bank, so the bank that the Swifties use, Bank of Taylor, whatever you want to call it. These are the people that have given them a credit card or a debit card. We then have our ticket merchant, the person that's selling our Taylor Swift tickets. And then we have our merchant acquiring bank. Now, this is a really important entity in the chain because it's our merchant acquiring bank that's authorized by the likes of Visa and MasterCard to actually go and collect the money on behalf of the ticket merchant. Now, if we think about demand for Taylor Swift tickets, our ticket merchants are going to know that there's millions of Swifties out there that really want to buy tickets. Our merchant acquiring bank is a separate entity in this chain. They're not going to have visibility of the number of people that have signed up for pre-sale. And they're a bank. They probably don't care. They probably don't care about Taylor Swift demand because they're thinking, we handle billions and billions of transactions every day, per second. We are scaled to handle this necessary demand. We have our scaling metrics in place. So if we think about how a merchant services architecture might be deployed in the cloud. So I'm just going to map out here our different actors in the chain. So we have our Swifties, we have our ticket merchant, we have our card issuer. Sorry, this screen's really high, so it's really difficult for me to see. We have our card issuer, our payment networks, and then our merchant acquiring bank. So our Swifties decide they want to purchase a ticket, add to basket, enter their credit card details, click pay now. So that request goes to our ticket merchant to say, I want to pay this amount of money. Now, if anybody is familiar with the Taylor Swift ticket saga, they were significantly more expensive than $100, but let's just, for the sake of argument, $100. So they communicate with our ticket merchant, who then sends a request to our merchant acquiring bank to say, hey, you're authorized on behalf of Visa or MasterCard to go and get this money for me, so please do. So our merchant acquiring bank gets that request from our ticket merchant. And what they do is that particular request generates an event, and they keep that event in some sort of event stream. In this case, we're implementing this in AWS, so we've decided to use some sort of event broker. We might use something like Kinesis, or we might use something else. But we're storing that event in some sort of event stream. The acquiring bank will then communicate over the payment networks back to the card issuing bank to say, hey, has this Swiftie fan got enough money in their bank account for this particular transaction? They will then send a message back to say, yes, they do. That again is another event that's stored in our event stream. Our acquiring bank then gets in contact with our ticket merchant and says, yep, all good to go. And then lovely jubbly, Taylor Swift fans get that congratulations screen with their reference payment, with their reference number for their ticket transaction. Brilliant, they've got their ticket. And behind the scenes, a clearing and settlement process kicks off between all of the different payment entities to make sure all the necessary ledgers are updated with these amounts. So our ticket merchant will then get in touch with their acquiring bank again and say, great, let's have the money, please. Again, more events in our event stream. There is then a clearing and settlement process that goes on where various messages pass between the card issuing bank, the merchant bank, over the payment networks to get the amount. You'll notice that the amount that actually goes back to our acquiring bank is not the $100 because it's less transaction fees. So just trying to map out a real world example here. But all of these events are stored in our event stream. But in this particular scenario, everybody's communicated successfully together, and our Swiftie fans have got their tickets, which is great news for them. But this particular example, what we're trying to do is we're trying to break up the different steps in the journey and have these event responsive or event driven steps that happen in our payment journey. And you'll notice that we have a little Amazon EKS symbol under our merchant acquiring bank. So for these particular payment, settlement and clearing systems, we want to containerize them and we want to deploy them onto Kubernetes. But before we jump into the Kubernetes setup and what that looks like, I just want to discuss a little bit what scaling on Kubernetes actually means and the different scaling dimensions when you have a solution that's deployed to Kubernetes. So just to baseline some of the components, Kubernetes control plane, so that's our Kubernetes API server, our scheduler, etcd. If you're using Amazon EKS, which is our Elastic Kubernetes service, we're going to manage this component for you from a scaling perspective, so you don't need to worry about that. Our Kubernetes data plane, these are our worker nodes or the compute that actually runs your containers. So think of this as like EC2 instances and storage volumes. And then we have our cluster services on top. So these are all of those add-ons and extensions that you deploy onto your cluster that extend some sort of capability to your workload. So something like, I don't know, Core DNS, something like that, for example. And then finally, we have your workloads themselves. In our particular scenario, we are particularly interested in how we can scale our workloads. So our workloads being our payment workloads that are going to grab the payment. And how can we scale our data plane or our compute, which is going to run those particular workloads. And when it comes to scaling our particular workloads, there are a few different approaches that we can take in Kubernetes. But they're really all, I suppose, concerned with how we can either A, have more instances of your containerized workload, so horizontally scaled, with the logic being the more instances I have of my container, the more work it can do. Or B, how can I give more resource to my container? Again, the logic being the more compute and resource it's got to access, again, the more work it can do. And there are three scaling approaches there: horizontal pod autoscaler, vertical pod autoscaler, and then Kubernetes event-driven autoscaling, or KEDA. Once you've scaled your applications or scaled your containers, you need somewhere for them to run, so that compute or that data plane. And there are two primary approaches we see customers using when they're using Amazon EKS for their Kubernetes clusters, and that is cluster autoscaler and then Karpenter. Let's have a look at application scaling first. So horizontal pod autoscaler. So this is entirely concerned with how can I increase the number of instances I have of my containerized application. So it works in conjunction with the Kubernetes metric server, and it looks at telemetry data such as CPU and memory. And based on a deployment definition that you have for your workload, it will make a decision, do you need more instances of that particular workload? At that point, it makes a request, and then the Kubernetes scheduler will then schedule more instances of your workload, and that essentially it looks like more replicas that run of your workload on your cluster. Vertical pod autoscaler works in a very similar way, again, in conjunction with our Kubernetes metric server, but rather than having more replicas or more instances of your workload, it simply increases the CPU and memory, so it gives it more juice, if you like. KEDA, or Kubernetes event-driven autoscaling, works ever so slightly differently. So KEDA works as a replacement, so to speak, for the Kubernetes metric server. So whereas our Kubernetes metric server is feeding telemetry data like CPU and memory, KEDA is going to be feeding really rich event-driven data. So KEDA has a number of integrations or hooks into some of the most popular integration tooling that's out there, many of which you will have heard about today, things like Kafka, for example, SQS, and what KEDA will do is it will expose metrics about these different integration services to our Kubernetes scalers to allow us to scale our workloads based on some event data. And how this works is by using what we call a scaled object. Think of this as just like a configuration, if you like, for KEDA. And then what we have are these things called scalers. And scalers will actually go and look at a given event technology. So let's say you're using something like SQS or Kafka or whatever. Your scaler will go and look at that event, event technology. We then have our metrics adapter. And the metrics adapter is going to grab data telemetry about that particular event implementation and convert it into a format that Kubernetes can understand. And then our controller will then act upon that and then feed information to our horizontal pod autoscaler. And what this means is that KEDA can pick up information about, say, a Kafka topic or a queue, and it can say, I've got a message in my queue. That's a scalable event that I want to do something on. And it converts that into a form that horizontal pod autoscaler can act on. I've got some configuration examples now of KEDA just to really demonstrate, I suppose, what it actually looks like. And I hope you can see it. This screen's a little high, but I'll sort of talk you through what we've got here. So this particular configuration is for SQS. So this is basically saying, I want to scale based on some information about SQS, so messages in my queue. And what we can define here are polling intervals, how often I want to poll my queue to see if there's messages in there. We can define what we want to happen if the queue is empty. So if we think about our payment architecture for our Taylor Swift fans buying some tickets, we really want to scale up the number of workloads that can handle clearing and settlement when there's lots of Taylor Swift fans putting pay now messages in the queue. But when they've all finished, actually we would quite like to scale that down to 0, because otherwise it's workloads that are running that we're paying for that aren't doing anything. I can also define exactly the URLs of the endpoints that I want to use. So if you have lots of different queues, lots of different queue names, you can also do that here. Equally, if you do have an event that you know in advance, you can pre-scale with KEDA. It doesn't always have to be responsive based on messages in a queue. You can also still scale on schedule. So if you know you have peaks for your systems throughout the day, you can still scale on a schedule using the information that you have about your end users and how they use your IT systems. You don't just have to be entirely responsive the whole time. So that's great to scale your workload. So rather than scaling based on CPU and memory, we now know that we could scale based on messages in a queue. And those messages could be Taylor Swift fans saying pay now, pay now, pay now, pay now. And that's what we want to scale under, which is great as I'm scaling my payment workload, but not so great if I don't have sufficient compute in my cluster to actually run all of those payment workloads. So that's where we need to look at data plane scaling. As I mentioned, there are 2 approaches that we see customers using for data plane scaling for Kubernetes. The first is cluster autoscaler, and the second is Karpenter. So Karpenter is relatively new. It was something that we developed in-house in AWS. It's fully open source, and we contributed it back to the CNCF at the end of last year. So it's now a graduated SIG autoscaling project. V1, so all its APIs officially baselined, happened about 6 to 8 weeks ago-ish. Karpenter is what we like to think of as application-centric scaling. So Karpenter will add compute into your Kubernetes cluster based on what your application needs, not necessarily based on what you've defined as a compute configuration. So it's specifically looking at what your application needs. And I'll explain what that means now. But before I do that, I just want to baseline how cluster autoscaler works, because we typically explain Karpenter by comparing it with cluster autoscaler. So it's always nice just to talk about how that works a little bit. So let's imagine we've had something that's either A, caused our CPU and memory to increase of our workload, or we've had a KEDA event, and that's fed into our horizontal pod autoscaler. So we now need more replicas of our workload. Kubernetes scheduler will attempt to schedule those workloads somewhere in the cluster. And if there is insufficient compute in the cluster, those workloads will be unschedulable. Where we have customers who are using cluster autoscaler, they typically use that alongside managed node groups, which is kind of configurations for like or similar compute in AWS. So when you've got your unschedulable pods, cluster autoscaler kicks in and it will pick a managed node group to expand. And under the covers of a managed node group is essentially an autoscaling group. So it will scale up some EC2 instances. Super easy where there's only one managed node group. If you have many managed node groups, which some of our customers do, it's a bit tricky then for Cluster Autoscaler to know which node group to pick. And there's a concept of expanders where you can give Cluster Autoscaler some hints and say, pick this node group over this one. But essentially, Cluster Autoscaler is making that decision. Some of the limitations that customers have raised to us about managed node groups are that they're very set in terms of the compute that's in there. So you have one managed node group per type of EC2 instance compute that you want to use. So say you want to use, I don't know, an M5 2XL, you'll have one node group for that configuration. And then maybe if you want to use another memory optimized instance or something else, you'll have to have a different node group for that configuration. And what customers found is that they just had lots and lots of node groups, and this was then doubled when they wanted to use things like a mix of spot and on-demand. So it became a lot of overhead to manage. And it was also a real pain when workloads were deployed to the cluster and they needed something which was not being served by the managed node group. So perfect example is you deploy a workload and it needs a GPU, and you don't have a managed node group configuration for a GPU. That workload is just not going to get scheduled and it's going to fail. So that's kind of where Karpenter really steps in. So if we think about our cluster autoscaler workflow, we have our pods, which will autoscale through our horizontal pod autoscaler. We have our pending pods. Kubernetes attempts to schedule them, can't. Cluster autoscaler kicks in, invokes the autoscaling group, adds more compute. In the Karpenter world, Karpenter is still listening to events that happen on the cluster. So it's a deployment to the cluster. It's continually listening for those unschedulable pod events. And when they crop up, Karpenter will then kick in and say, great, I need to do something. I need to scale the compute in this cluster. And what it does is it looks at all of the unschedulable pods. It bin packs the amount of CPU and memory that those pods need into kind of two metrics. And then it makes a decision about the right type of EC2 to pick in order for those workloads to be scheduled. And it does this using two strategies. So if you want to use on-demand compute, it will pick the cheapest EC2 instance. If you want to use Amazon EC2 spot instances, it uses something called a price capacity optimized strategy, whereby it looks at the spot pool, which is biggest, and then the one that's cheapest. And then what it does is it communicates with our EC2 Fleet API. And this is a synchronous call that it makes, so it gets an instant response back. Our cluster autoscaler using autoscaling groups makes a call just to our regular EC2 API. And this is an async call. We haven't done any benchmarking on the times in terms of response times, but we do have some of our AWS heroes that have, and there is a blog that exists. Definitely go and have a look for it. But one of our container heroes did a benchmarking exercise trying to scale to 10,000 pods and comparing all of the different scaling mechanisms, and did find that there was a performance improvement in terms of scaling to 10,000 when using Karpenter over cluster autoscaler with managed node groups. So if you're thinking about it, definitely benchmarking that you should be aware of. So Karpenter basically makes that decision of what compute to add into your cluster. But you can still give Karpenter some guidance. We have a concept of a node provisioner template where you can tell Karpenter, for example, don't pick bare metal instances or don't pick T2 micros, to give Karpenter some guidance about what to pick. Equally, you can give Karpenter some further guidance that says, when you do spin up an EC2 instance, make sure it's labeled in this particular way, make sure it uses this API, AMI, etc. And you can do that with a node class template. And what this allows you to do is it allows you to move towards compute that's driven by your workload. So you're not going to spin up an EC2 instance that's based on a static EC2 config. You're now looking at what your workload wants. So say you have 10 unschedulable pods you're going to spin up an EC2 that works for those pods, maybe not just an EC2 that's defined by your configuration. And it means that this means you can be a lot more flexible with the type of compute that you have in your cluster. And if cost is really important to you, Karpenter uses a bunch of different cost optimization strategies to be able to pick the cheapest EC2. And there are a couple of different strategies that Karpenter can use in order to pick the right instance. But I just want to step you through, I guess, the Karpenter config and what it looks like. So in this particular example, we can tell Karpenter which type of EC2 instances we do and don't want it to select from when it makes a decision. Because Karpenter's considering our whole EC2 availability. So that's like over, I think the last count, it was over 700 different options that you have. So Karpenter has all those 700 to pick from, and this is a great way to give it a bit of a steer as to which one. Another thing I want to draw your attention to is the config right at the bottom, which is a CPU limit. So Karpenter no longer wants to think about your Kubernetes data plane in terms of the number of nodes. It wants to think about it in terms of the number of CPUs that your workloads need. So Karpenter doesn't care if you have 1 node or 10 nodes, as long as you have the number of CPUs that your workloads need, it's happy and it's satisfied. And what we're trying to trend towards here, I suppose, is shifting that mindset from my compute layer is a set number of EC2 instances, and we want to shift towards our compute layer is this much CPU and memory for my workload, and really be workload driven when we're thinking about it. We can also tell Karpenter about things like availability zones to make sure you're keeping in mind best practices around architecting for resiliency. Equally, we can tell Karpenter if we want to do things like use different types of architecture types, whether you want to use Intel, whether you want to use Graviton, whether you want to use something else. You can tell Karpenter to do that. Equally, you can also specify if you want to use spot on-demand instances or both, if you're thinking about your different purchase options. So it's a super easy read in terms of the configuration. But it's a different way to think about scaling your data plane, and not necessarily just scaling your Kubernetes data plane based on like a static config. So we have a really cool example on our GitHub page, which will allow you to create a Kubernetes cluster using Amazon EKS with Karpenter and KEDA set up and configured on it. So there is a link to our GitHub repo. There's a nice README file. It will step you through how to set it up. So if you're interested in what that architecture could look like, here's a really good example. But let's bring this now back to Taylor Swift. So we've had a few minutes now where we haven't mentioned Taylor or our very sad Swifties who weren't able to actually make their payment transactions when they were buying tickets. So how does any of this actually help our Taylor Swift problem? So let's think about our fans. We've got our fans, and they really want to change their lives by buying some tickets. And the way they want to do that is with a credit card transaction. So really what we want to happen is our credit card transaction systems and all of those dependent systems that we saw in that chain earlier on, we want those systems to actually scale based on the Taylor Swift demand. We don't want those systems really to scale on CPU and memory. We want them to scale based on the number of Taylor Swift fans that have clicked pay now and given their information in. And we now know that KEDA is a way to do that. We now know that if we have an event stream with lots of different events in, KEDA is one way that we can read information from that event stream and scale based on it. So KEDA is a key part of our solution here. So what does this actually look like in practice? Now, I do apologise, this diagram is a little fiddly. So let's think about our Taylor Swift fan. So our Taylor Swift fan is right at the top on the left-hand side of this slide, making a credit card transaction. So the credit card transaction message has gone into the queue, and we have our workloads that are deployed to Kubernetes that are processing that message and then persisting some data somewhere and communicating with our merchant bank to say, you know, let's make this particular transaction. But let's imagine we don't just have one Taylor Swift fan anymore. we have 4. Or in the case of our problem, 4 times the amount of peak traffic. So think of this as actually millions of fans that now suddenly want to purchase a ticket. So we now have loads more messages in the queue, and we don't have sufficient instances of our application to actually process this. So really what we want is KEDA to look at the queue and recognize that we need more instances of our pod. So we have KEDA here in the center of our slide, recognizing that our queue size has actually increased. So KEDA communicates with our horizontal pod autoscaler. It does that through that metric server and that controller, and says, hey, we need more instances of our credit card transaction processing workloads that we've got. So we've now got all these pods that the Kubernetes scheduler needs to schedule. And then Kubernetes realizes, oh no, we've only got two EC2 instances. That is not enough compute for all of this. So at that point, what we want is Karpenter to kick in and realize, hey, we need more compute. And not just we need another 2 EC2 instances, we need compute that's big enough to look after all of these 5 pods that are unschedulable. So Karpenter will then look at what the pods need. It will then look at what's cheapest if we're using on demand, or the cheapest with the biggest capacity available if we're using Spot, and it will then provision the right EC2 instances. And in this particular example, it's worked out the cheapest thing to do is to provision small EC2s, but 5 of them. But perhaps on another point in time, the cheapest thing to do could have been to provision a single EC2 instance. But Karpenter has now provisioned those new nodes. Kubernetes scheduler has scheduled those workloads on those nodes, and we're now processing all those messages that are in the queue. So our Taylor Swift fans now are happy because they're all receiving transaction complete messages, and they are getting access to their particular tickets. So we've sort of solved the Taylor Swift problem. We've solved the bit in the journey whereby we have dependent systems that maybe don't know about the demand of the pre-sale. They don't know how many fans have signed up, but they want to make sure they can handle it if that ever happens. Now, when it comes to scaling based on event-driven metrics and scaling with Karpenter and with Kubernetes, there are certainly some best practices to keep in mind. All of those are detailed on our Amazon EKS best practice guide, which is where this QR code will link to. But really, we want to encourage you to think about the most optimal, compute configuration that you need in your cluster for the workloads that you actually want to run. So definitely have a look at the best practice guide. There's a really interesting configuration on there. Check out our GitHub repo, which gives a really good code example of this particular setup. And all I'll say is thank you for your attention. Good luck for any future Taylor Swift fans out there that want to try and go and see Eras 2. Thank you very much.